So to continue discussing ways in which hypothesis testing is connected to other things that we've been doing so far in this class, I want to talk about this test statistic. So remember, when we're doing hypothesis testing, the first thing we always have to write out are the hypotheses. You have your null hypothesis, your alternative hypothesis. After that, then you have to figure out which tests are you going to use. So that requires you to figure out, are you looking at means or are you looking at proportions? Are you looking for a one sample? In the future, we'll be doing two samples. So right now it's just one sample. And then do we have a known population standard deviation or unknown? If we're dealing with means, when it comes to proportions, we just simply know if we have a one sample proportion, we know the exact test that we're going to use. And then we could also indicate things about it being a one-tailed test or a two-tailed test, or in particular, we could do a left or right-tailed test. Now, once we have all of that figured out, then what we've been doing is we could just plug numbers into the calculator once we know if it's going to be a z-test or a t-test or a one-prop z-test, and then magically things pop out. But let's figure out a little bit of the behind the scenes of that magic to understand where are these values coming from based off of things that we've been doing so far in this class. Okay, so the test statistic, remember, so this is something that the calculator just pops out for us that we want to be able to use properly and indicate. But the test statistic, what's happening of how this appears is that it can be found by using the central limit theorem for means. So what I'm looking at in this case is if we have means with one sample and we have a known population standard deviation. So that's one that we've done the most amount of work on, so we're going to continue to work with that example. So we have this normal distribution. Sample means are normally distributed, where we have mu sub x as a mean and sigma sub x divided by the square root of n is our standard deviation. So let's take a look at this example. So suppose the average weight of all 10-year-olds in a school is 78 pounds. The population standard deviation of weights of 10-year-olds is normally distributed with a sample or population standard deviation of 8 pounds. Sterling School District thinks that they have an average weight greater than 78. They collect a sample of 16 students and found the mean to be 84 pounds. So you could do hypothesis testing on this. You would need an alpha value to define that, to figure out if we reject or do not reject the null hypothesis. But we're going to start to get through some of the other computations and not so much worry about the end result of do we reject or do we not reject. I'd like to look at the test statistic, and then with that, we're going to see a little bit of things with the p-value. Okay, so if we did hypothesis testing, our null hypothesis would say mu is equal to 78, saying that Sterling is no different than the average. Our alternative hypothesis would be that mu is greater than 78, saying that no, indeed, I think that we have a average weight that is larger than 78. All right, but let's take a look at what this would look like if we re-envision this back when we did central limit theorem for means with this. So we have this x bar is approximately normally distributed, where the mean that we have of the population in this case, our population mean is assumed to be 78. And then our population standard deviation in this case is 8. And our sample size is the square root of 16. So we're saying that x bar is approximately normal with 78. And then we take 4 divided by the square root of 16. So we take 8 divided by 4, and that gives us 2. Okay, so this is what our normal distribution would look like for the central limit theorem. So then if we think about visualizing this, what we have right in the middle is 78, and I am looking at my sample data I collected was 84. So with this picture, automatically, hopefully, there's some things that come into your mind of, oh, wait, I could probably find z-scores. Oh, I could probably find different areas and things. So let's take a look then at what would that look like back with the central limit theorem. So we can find the z-score of this. So remember, our z-score is always the data value minus the mean divided by the standard deviation. So our z-score, the data value we have is 84. The mean we have is 78. And our standard deviation in this case is 2. Remember, we're using the central limit theorem, so we divide this by 2. So I get 6 divided by 2, which is equal to 3. So you could now use the chart if you would like to. So if you still have this handy dandy chart here, you'll be like, hooray, I remember how to use that too. You look over here at a z-score of 3. And so in our picture, what we have is, so we have 78. We would have 84. Using this chart, we see that this area right here would correspond to 0.49865. So then this here would be 0.5 minus that, so that would be 0.00135. So that is what it looks like if we kind of ignore the hypothesis testing part and instead view this in light of our central limit theorems. Okay, now if you are able to work through this though with hypothesis testing, even though I haven't given you alpha, we could still do enough to figure out what is going on with this hypothesis testing. So if we look at it with hypothesis testing, our null hypothesis says that mu is equal to 78, and our alternative says that mu is larger than 78. So then if you type all of this into your calculator, and you, in this case, since you have a known population standard deviation, you're going to use a z-test. So if you use a z-test with all of this, what you would find that pops out is a test statistic that says z is equal to 3 and a p-value that is equal to 0.00135, at least if I round that. So notice this test statistic is exactly the same thing as our z-score that we found before. And notice that this p-value is exactly the same as this area that's out here. Because remember, the p-value, that's the probability that we have another one that is as extreme or more extreme as our sample that we just collected. So in this case, because the alternative hypothesis is larger, we had this area that we could imagine shading in, that's what it means to be more extreme. So in this case, our p-value is exactly that area over there. So these numbers that are appearing from your calculator when you're doing a hypothesis testing, the test statistic and the p-value, these are all things that you could do by hand again if you wanted to. Obviously, we're not going to do that, and nor would I encourage that whatsoever. But you have the tools in your abilities to be able to take care of these by hand. I guess as a note, we are, again, working with the normal distribution. When it comes to the student t-distributions, we didn't have any other way to do that besides using a chart. So, but at least you could do something similar if you're more familiar with student t-distributions. Now, the last thing that I do want to mention, that in this class, we're going to be doing hypothesis testing by looking at p-values and making decisions of this based off of alphas. But there's a different way that, especially when you understand it through this, you could also do this via critical values. So for instance, if you're looking up things online, you might see the term critical values appear. What that's going to say is for any alpha value, you always know what the area, say, to the right would be, or the area to the left, or both of them combined. So given a certain alpha value, we're able to always have some comparison of what that z-score would be for a given alpha value. So for instance, if alpha equals 0.05, we could always have a critical value, the z-score, that we could compare it to. So the test statistic often gets used in that comparison. And so you'd compare the test statistic to this critical value associated with the alpha value, as opposed to using p-values. Now, you don't have to know any of that, but just in case you're looking at other resources online and you see things that they're not using p-values and they're instead using the test statistic and critical values, then that's what they're doing instead. But I encourage you in this class to focus on learning how to use the p-values and make the decisions off of alpha.